Hello everyone, today I want to talk about a tunable sensitive comparator for two signal inputs. Comparator is a commonly used unit for comparing the signal strength of two different inputs. It's very easy to construct by using electronic device, but there are only a few research about how to construct it in synthetic biology field. But it can be potentially a very powerful tool in synthetic biology. Any biological process about like comparing two signals and then making decisions can use the comparator. For example, during the process of development, we can compare the concentration of two different morphogenes and then choose to develop into different kind of tissues. Besides, we can also use comparator to do some simple subtraction. The main idea here comes from the complementary property of RNAs. If two RNAs can complement each other, they will both lose their function as a single-strand RNA. So if we use two inputs to give the expression of two single-strand RNA, the complementation of the two RNAs will make them both unavailable for the downstream gene expression. So only when the two inputs are different, the excessive RNA can properly function as activator or inhibitor. According to the literature review, I found that I can use a small transcription activation RNA, which is called STARS here, to activate the downstream gene expression. STARS work by binding with terminator or attenuator before the coding sequence. Or we can rationally design it to bind with the SD sequence so that we can inhibit the downstream gene expression. Here is an illustration for my design. The STARS1 and STARS2 can be controlled by two inputs, and they will inhibit each other through the base pair interaction. When the input 1 is over input 2, the amount of STARS1 will be over the amount of STARS2. So most of STARS2 will bind with STARS1. So only GFP can be expressed, and both the expression of RFP and YFP are inhibited. When the two inputs are about the same, the GFP and YFP will not expressed because of the two stars inhibit each other, and the YFP will be expressed because there is no inhibition anymore. Then I try to write some biochemical reactions of this system. To make life easier, the stars 1 is simply proportional to the strength of input 1, because we will focus on how this system works rather than where the inputs come from. Then the stars 1 and stars 2 will bind to each other, and the complex also dissociates into these two RNAs. The equilibrium is determined by the binding and dissociation constant. This is what we need to focus, because by changing the sequence of two stars, we can change the equilibrium of this process. We can predict that if the binding of two RNAs is tight, there will be less free RNAs, so our system can be much more sensitive to the inputs. But when the binding is loosened, the differences between the two reporter genes will be much smaller, which means our system will be less sensitive. The STARS1 and STARS2 can bind with the activation elements between coding sequence to activate the transcription of downstream genes. And also they can bind with the inhibition elements to inhibit the translation process here. And I write the differential equation to describe how the whole process works, and also for this kind of process like translation and degradation. Then I use the MATLAB to stimulate the whole process. The first step is to validate whether our system can work well. We can see that when the ratio is lower than 1, which means the amount of STARS2 is more than that of STARS1, the expression of RFP will be much higher than that of GFP, and it can be higher than YFP when the ratio is below below than 0.9. When the ratio is bigger than 1, the expression of GIP is much higher than that of RIP, and will dominate when the ratio is more than 1.1. Also, we hope that we can check what will happen if we change the binding constant. As we accepted before, we can tune in the sensitivity by tuning the binding constant. So we can say that as the binding constant increase, the GIP expression level will be much lower when the ratio is low, and it will stay the same when the ratio is above 1, which means that when we change the input ratio from 0.9 to 1.1, there will be more fold change for higher binding constant. And it also works for RFP. We can say that if it changes from like 1.2 or 1.1 to 0.9, there will be more fold change for binding constant of 10 than binding constant of 1. And for YFP, things are slightly different. You can say that there will be slightly increase for all of the ratio if the binding constant increase. This makes sense because the bigger binding constant means that there will be less free RNAs wandering around the space. So there will be less inhibition for the expression of YFP. So if the binding constant increase, there will be more YFP being expressed. Apart from that, we also want to know the robustness of our system. So here I introduced some leaky expression to check what will happen if we have some SARS-2 leaky expression. In this case, I stimulate the situation that both SARS-1 and SARS-2 have a basal leaky expression for 10% of inputs. And then we slightly increase the leaky expression level of SARS-2 to say what will happen to the gene expression as the ratio of inputs change. The result here is very obvious. The balance slightly shift from 1. And for GIP, it means that it needs to produce more SARS-1 to balance the leaky expression of SARS-2. However, if we have more differences for the two inputs than the differences between leaky expressions, the system can still work very well and still keep sensitive. And the peak expression of YFP will also shift. Considering that in the reality the differences between two inputs will be likely more than the differences of leaky expression. So the leaky expression may not disturb the behavior of our system, and it will not disturb the sensitivity of our system in any case. Last but not least, let's take an overview and to check the behavior of our system. Let's take an example. Like for a ratio of 1/2 input level, like for input 1 it have 0.5, and for input 2 it has 1. The GIP concentration will be like 10 to the 3rd, which is the RP concentration will be 10 to the 12th. So our system will have over 9 log units for the change in total. In the reality, the situation is very possible, which means that for most of the case, we may have over 9 log units for the change for only 1/2 ratio. And the results also indicates that our system is an ultra-sensitive system, and we can give a high response to even very small differences. So in conclusion, our system can compare two signals and give appropriate output. And by tuning the binding constant, we can tune in the sensitivity and fold change. Our system will be influenced by the leaky expression because it's very sensitive, but it can still work very well when the differences between inputs is larger than that of leaky expression. Most importantly, it's very sensitive and give very high response to the even 1/2 ratio differences. That's all. Thank you.